right, I'm going to introduce our guest speaker today. It's with great pleasure that I introduce Chuck Huber. He's a good friend. We cannot remember how we met, but we've been friends for several years now. So he is a senior statistician at StataCorp, or I call it Stata. He calls it Stata. So potato. And he's been gracious enough to come and give us a lecture on the topic of my choice, and my choice happens to be multi-level modeling figure. That's something that for a lot of people, they struggle with. It doesn't matter if you've been a statistician for 20 years, and we're having this talk about this, that sometimes the most complicated issues around, or the complicated aspects of multi-level modeling, just explaining. Try and explain to somebody what a fixed effect is and a random effect. And you could try to verbalize this for 45 minutes and they won't get it. And Chuck has got some slides. They're beautiful that they do that very nicely. But I thought this is a topic that, first of all, health service researchers, we're always dealing with things that are nested, where they're nested patients in physicians and clinics and hospitals and centers and whatnot. And we have it throw in there the time component on it. This is something that we all need and use. And probably few of us know it well enough to be conversant to be able to explain what a fixed effect is and a random effect, or random effect on different levels. So I thought that was like a really nice way of starting Chuck's sort of foray into IHPI, because he's also gracious, and well, it depends on how well we treat him today, he's agreed to come back in the fall and give us even a larger array of presentations on different topics. And since we're primarily a Stata house here, I know there's others that use R and SAS, but at our core, we're Stata users. So the way this will go is like the first hour, it's an overview. So if there's investigators, primarily for investigators that don't necessarily need the nuts and bolts of how to do this, but want to be able to understand better what a fixed effect and a random effect is, and especially when you bring in the levels. That'll be a nice overview. Little math, there's some equations, but not the math underlying it. And then sort of roll that into the second hour, which is, okay, now let's bring on this, open up Stata and show you how you actually do this and how do you interpret the output files. So I anticipate we're gonna have some people staying and some people going, but it'll be a little bit more, it's going to be all-encompassing for both investigators and analysts. And I would say if they're free, they ask questions as they go, or
sure,
right.
Just fire away.
All right, I think that's it. We'll let Chuck start off.
Thanks, Ariel, and thanks for having me up. I wanted to just come up and hang out, so I wish I was going to be here longer. So, yes, we're going to talk about multi-level modeling today. I've been running around for the last month talking about Bayesian item response theory. And I was going to come here and talk about Bayesian response theory and Bayesian item response theory. And Ariel said, hey, we'd really rather hear about multi-level modeling. But then I have to prep a new talk. So long story short, I would only do this for Ariel, maybe a couple other people. So there are only a handful of people I would just do a one-off like this for. But it's such a fun topic. And I had sort of the base of these slides kind of already put together, and so I went through and expanded them. What's going to make this talk interesting is I haven't done this talk at all, in the sense that I made these slides, I finished them at when did I email you, 4 a.m. the night before last. I haven't slept much. So, and I haven't actually gone through these slides. So we're going to proofread my slides together, if you don't mind. There may be some typos in here along the way. Just out of curiosity, how many, and it's fine if you're planning to leave, how many of you are planning to stay for the second hour? So I wonder how many people are going to show up next. As Ariel was saying, we're going to go through just a conceptual introduction for the first hour and then kind of cut it off and then go into the second hour and talk about how to do this stuff. So we may be able to cut out some of the, if it's mostly just this group that's here for the second hour, part of the beginning is redundant. We'll just cut through that and blaze on through. We may be done a little early if possible. How many of you do multi-level modeling? You actually do this on a sort of regular basis. How many of you would like to do multi-level modeling? It's just kind of a mystery. It's okay. Well, we're hopefully going to demystify this some today. I am from StataCorp, by the way, and so I obviously think Stata is pretty cool. So what we're going to do is we're going to go through just a very conceptual introduction to single-level models, two-level models, And a lot of people treat longitudinal data as multi-level models as well. So we're going to talk about longitudinal modeling, and we're going to talk about 3-level models. And once you get to 3 levels, if you can do 3 levels, you could do 4 or 5. Conceptually, it's the same idea. But you rarely see, I rarely see anything beyond 3. I don't know about you guys, because it just breaks down. You don't have data sets that have that sort of a form. But if you can do 3, there's no reason you couldn't do 4 or 5, at least in theory. And then I want to try and demystify this notion of fixed versus random effects. I find this is confusing to people who've even been doing this for a while. You know, when do I use a fixed or when do I use a random, and what does that mean? And if you're an economist, it may mean something. How many of you, we should get that out of the way. How many of you are economists? Any econ people in here? A friendly audience, all right. Okay, just so you're aware, economists use the terms a little bit differently, fixed and random, and we're going to come at this from more of a biostatistician, I'm a biostatistician by training, that point of view. And once you can do this for continuous outcomes, it's a short leap to being able to do this for binary or count or ordinal or multinomial outcomes. We're not going to talk about some of the complications that go with that. If you're familiar with over-dispersion and those things, we're going to just sort of move on past those topics. The other thing that I want to talk about is multi-level survival data. This happens more often than you'd think, so we're going to just kind of do a glancing blow at that. Structural equation modeling. Anyone use structural equation modeling in their day-to-day life or familiar with it? Okay. Turns out in Stata now you can fit multi-level structural equation models, and so I'll show you why you may want to at least explore this. And then the last thing I want to talk about is Bayesian multi-level models. Bayesian statistics has become more and more popular over the last probably 10 to 20 years, certainly in the last 10 years. So we'll touch on that very briefly. By the way, if you have questions along the way, please just jump in. We'll make this as informal as possible. Okay, so I thought before we start talking about multi-level models, let's just back up and talk about single-level models for a minute. So here's some notation. Let's imagine that we have a bunch of patients and we collect some sort of observation on these patients. Doesn't really matter what it is, but these red dots here are going to represent observations on some patients. And I can refer, I'm going to need some notation. So when I refer to y I'm going to use as the outcome variable, the thing I'm interested in. And I is going to simply be an index that indexes which patient that I'm talking about. So that's all the subscripts are there for. I just need to keep track of which observation goes with which patient. Now, the simplest conceivable model you could have for observations like this would simply be that each observation is going to be equal to some grand mean plus some error. Each of the observations is off by some amount. So for instance, if I were to take this observation right here, I can describe that observation as being the mean plus whatever its error term is, okay? So that's all that is. And every single one of these points I can describe the same way. I could pick this point and describe it as the mean plus whatever that deviation is. So notice that each E has an I, it has a little subscript, because every observation is going to have a different error, a slightly different error term. So that's a way of thinking of single level data. It'd be just like computing a sample mean. Now some notation or some jargon here. The Y, the outcome part, is the observed part of the model. When we go to start modeling these things, the data itself is what we observe. And what we're going to do is we're going to break that into 2 pieces, these observations. There's going to be a fixed part of the model, which could be something as simple as a sample mean, or it could be something as elaborate as a wild regression model with lots of covariates and things like that in it. But that's going to be the fixed part of the model. And I'm just going to use mu to generically represent all of that, whatever it may be. Sample mean, wild regression model, whatever you want to call it, that's going to be the fixed part of the model. The random part of the model are these error terms, these residuals, the how far off am I, how far off is my observation from that fixed part of the model, from the mean. And actually, this is the essence of all things statistical, if you think about it. All things in statistics essentially break things down into here's what I observed, here's some model that I've built, the fixed part, here's some model of the data, and then I'm off by a certain amount. And how far I'm off is the error term, the residuals. And that's what most of statistics is really all about. But this is the jargon we're going to be using. We have observations, a fixed part, and a random part. So we can talk about distributions of these errors because the mu, the fixed part, that's going to be the same. Okay, that's the same. The average is the same for all of the observations of all of the participants. But the errors are going to be different for each person, and we can have a distribution of these error terms. By the way, they're not mistakes. residuals is probably a better term to use, but for whatever reason we use E. So these error terms will have a distribution. And we typically assume that these error terms have a normal distribution of some kind. And in a regression context, we assume that these have a mean of 0, because the mean is whatever the fixed part is. So the error terms have a mean of 0, and there's some variability of these error terms. So that's the general idea of a simplistic view of single level data. We calculate a mean, we have some errors. So how do we elaborate this to a 2-level model? How is this different? Well, the classic example of multi-level data, or the idea, is that you have data that's nested in some fashion. The observations are clustered in some natural way. So one way to think of this might be patients within physicians. So each of the red blocks now is representing an observation on a particular patient, and the green blocks up here are representing physicians. So one group of patients may be all seen by the same physician. Well, that often, not always, but often can induce correlation within the observations, induce correlation within the nesting level. So for example, if a bunch of patients go to the same physician, maybe that physician is a particularly good physician, maybe they're better at motivating their patients to eat better and exercise or whatever, but there may be some physician level effect to the health or the outcomes of the patients within that physician. Maybe you have another physician who's just overburdened, or they don't have time, or they're not as good, or not as motivated, or whatever. And so the patients nested within that particular physician may have different outcomes that are influenced in some way by this nesting structure. And so that's why we want to take these things into account. We'd like to incorporate that upper level, the nesting, into our models to take that into account. So how are we going to go about doing that? Well, the first thing we need to talk about is some sort of jargon, and it's multi-level models. So traditionally level 1 is this bottom level, the finest level of resolution in your data set. The second level, or level 2, would be one step up from that. If we had a third level, we would call that level 3. So we start at the bottom and work our way up in terms of levels. We also need some notation. This you will see different ways in different books depending on which book you pick up. Sometimes you see it done YIJ, where I indexes physicians and J indexes patients. So it goes level 2, level 1 this way. Some textbooks go the other way. Some reverse it, it would be J and I here. It's the same idea, it's just a way of keeping track of which observation goes with which particular patient and physician. So I and J, and all these, when you see these in books, these multi-level models, you get this blizzard of subscripts, and it can become very intimidating. But just remind yourself that all those subscripts are there for us to keep track of which observation goes with which patient and which physician. That's all they're there for. So don't let the subscripts intimidate you. So just like we had last time, we have patient observations within a particular physician. So this might be one physician's group of patients. So I have person 1, patient 2, patient 3, patient 4, I have 6 of them, all seen by the same physician. So I can talk about a physician mean. If I were to take all of the patients among that physician's patients, I could calculate a mean just for that particular physician, right? So this might be that physician's mean. And if I did this for each physician, now I have this physician's mean, I have another mean for this physician, and then another mean for this physician, and so forth. So I have all these separate physician means. And then I have this overall grand mean right here. And so I can talk about the deviation of these things, each observation, from the overall grand mean and from the patient mean. And that's what I'm going to be doing. That's what differentiates this in terms of the modeling, is rather than talking, if I pick out this observation right here, and I want to talk about that particular person, that patient deviates from the grand mean by a certain amount. That's just like the single level model. With the 2-level model, what I want to do is I want to partition that deviation into 2 parts. The first is the deviation of the observation from the physician's mean, their particular physician's mean. And then I want to talk about how far away is that physician's mean from the overall grand mean. So I've taken the same residual. It's still the same residual. I've just broken it into 2 pieces, okay? And that's how I've represented this, and I've color-coded at the bottom here in my model. So now, see, we've got a typo. That should be just Yij. It shouldn't be a K there. So Yij is going to be equal to the mean. If you think about that observation, that's equal to the mean plus its deviation, the deviation of its physician's mean from the grand mean, And then I have a little bit for how far this particular observation is from their physician mean. That's all it is. Now, this is a slightly different way of writing this than you will see in, I wouldn't even say most, I'd say any textbook on multi-level modeling. The way this is typically written in textbooks is you'll see some funny Greek letter here, and then the Greek letter down below that will be equal to some physician-specific mean plus some error term for it. You can write it that way, and it's the same thing. I just think this is an easier notation. It's an easier way of writing it, and I think it's unnecessarily complicated to write it the other way, which is unfortunately the standard way it's written in textbooks. But that is literally all it is. Now, what we've effectively done then is made the random part of the model more complex. Typically, we're interested in the fixed part of the model, right? We want to add in covariates, age, sex, race, things like that. And so we typically focus on the fixed part of the model. But for multi-level models, at least in the beginning, we need to spend a little time focusing on the random part. So we're going to make the random part a bit more complex. Both of these random terms, the UI dot, the dot here, I should have mentioned this earlier, UI dot means I only have these physician deviations for each physician, right? I don't have them for each individual. So the dot means that I'm ignoring that bottom level. So let's say I had 3 physicians, which I do in my example data set. I'm going to have U1 dot, U2 dot, and U3 dot, because this is only indexing physicians. U only happens at the physician level. So I don't need to take into account each observation. I don't care about them at level 2. I do, for the error terms, they're indexed as UIJ because I do have to have one for each of the observations. Both of these random terms in the model are assumed, and this is an assumption that we make, and we really ideally need to check this. We assume that these have, if we were to add them or look at the distribution of them, that they have a mean of equal to 0, and that they have some variance, and the variance is estimated separately for each one. So often you'll see sigma squared used for the error term variance, and something like tau squared or some other symbol for the upper level, second level variance. But the point is, we are going to have these at different levels, and we're going to have to make some assumptions and estimate the variability of these, which is partly why they're called random, because we're estimating the variance of them. We're not just estimating a particular value, a fixed value. Any questions so far? I know this is a really strange way of looking at this, but hopefully a clearer way. Okay, so let's talk about longitudinal models. Sometimes we have repeated observations within patients. So it's actually very natural to just simply think of the observations as being nested within people. It's the same idea, right? Physicians and patients, we have observations within people. Conceptually, there's nothing different about this, and mathematically, there isn't either. So if I have these observations nested within individuals, obviously repeated observations within an individual are likely to be correlated. We take your blood pressure every week. Your blood pressure is going to be very similar if it's coming from you, much more similar than if we took my blood pressure and your blood pressure and someone else's. It's going to be correlated because it comes from the same person. So again, we're going to use this level notation, level 1, level 2, exactly like we did before. And we're going to use, some people use T for repeated measurements for time. So sometimes you'll see this abbreviated or indexed as YIT. Rather than using I and J, you'll see I and T, where T is indexing time or the repeated measurements. But again, it's the same idea. So again, we have the repeated observations within a patient. If we have 6 measurements taken on a person, we can average those, average the observations within a particular person. So now this is a particular person's mean. Okay, not a physician. This is the actual person's mean of the repeated observations within that person. And then just like we did before, each person has their mean, and that person's mean deviates from the overall grand mean in some fashion. And then I can do this exact same exercise I did before. So I have each observation, YIT, now it's a repeated observation. It deviates from that person's mean, the patient's mean, by a certain amount. That patient's mean deviates from the overall grand mean. And I'm right back where I was with the 2-level model. So if you're looking at this and saying, wait, that looks just like the slides you just showed us, it is. It's because it's exactly the same thing. There's no difference. Longitudinal data is just another kind of multi-level model. And so that's the point I wanted to make by showing you these slides twice in a row with different labels. It's literally the exact same thing. Okay? Modeling longitudinal data is just a 2-level model. Okay? So you can change the subscript from EIJ to EIT if you want to sort of emphasize that, but other than that, there's no difference in the modeling of these things. Now, if you want to become more sophisticated though, and you want to include covariates, which you're going to have to do to take time into account, the multi-level part is done, but now we need to start talking about making the fixed part of the model more elaborate. Because right here, we've taken into account the correlation with the random part, the nesting structure. But now if we're going to model longitudinal data, we also need to take a look at the fixed part. So all I've done is in this slide is I've taken that, all those little humps and things, and I've flipped it up on its side. So this is exactly this thing right here. It's exactly the same thing. All I've done is flipped it up on its side. So I'm still paying attention to the same observation right here, and the same observation deviates from the patient mean deviates from the grand mean. But by flipping it up on its side, now I can start thinking about this in terms of regression. So I still have a grand mean, okay? But now I have this horizontal axis that shows age in years. And then the example I'm going to show in the second hour, age is going to range from, I think, about 30 to 50 years, probably more like 40 to 50. But anyway, so what I've done here is added a horizontal axis. But other than that, nothing's changed. The model is still the same. YIT is equal to this grand mean right here, plus some deviation for a particular patient, and then that patient's observation is off from that patient mean by a certain amount. Same exact thing. I can change mu now to a beta 0, just to emphasize the notion that I'm doing regression now. But it still looks the same. Everything's just sort of flat. The mean is the same across age. So what I need to do then is add an age to the fixed part of the model. See here at the top where I've added a beta 1 plus age. So this is going to allow for a slope, a change of blood pressure, whatever the outcome is, over age. But all I've done is added that to the fixed part of the model. So all of the lines are still parallel. And you can see why that would happen, because the only slope comes from age. But the UI part, the upward deviation, is the same regardless of age. It's not a function of age. So all of these lines are going to be parallel. So the grand mean it's a slope, and it's parallel to the patient mean. And we may be interested in changing that. So let's take a look at, for example, if I have this slope for all patients, that's the average slope, which is what I've done here. By adding this beta 1 term, that's the average slope for everyone in the entire data set. But what if I were to plot, excuse me, a cloud of points for just one person? Let's say that cloud of points is one person's data over time. And I look at that average slope for everyone, and I say, well, that is kind of close, but it looks like I could fit a better line to that cloud of points for that particular patient if I wanted to. And in fact, I can do that. One of the things you could do with software is you can, in addition to estimating an overall mean for everyone, an overall slope, you can fit a little regression line for every single person in the data set. And that's what what's called a random slope is doing. We've gone through for every person and estimated a separate slope for every person in the data set. So there's an overall average slope for everyone, and then there are these individual. So green is common to everyone, but the brown line here is going to be unique. There will be a separate brown line for every person in the data set. And so that's why this brown line here, I've added in another term, which is this U1 I dot for age. It's a function of age. And it's indexed because that line, again, will be different for each person in the data set. So now, if we look at our errors, at what's going on with our residuals here, here's how we build up this equation. Sorry, I've got this K in here again. I need to clean this up some. So now, what my model here says, I have this particular observation. That observation is going to be equal to some constant, okay, this grand mean, plus the slope for age, so that's this black line, the beta 1 plus beta 0 times age, plus some deviation for the overall patient mean. That patient deviates from the overall grand mean by some amount, so that's part of the model here. And then that's the overall slope for all people. But I've now fit a separate slope for each person. So for this particular person, I have a deviation from the overall average slope to the slope for that particular person. So I'm going up a little bit further here. Now, notice that brown line, the reason I have age in parentheses next to that is because it's a function of age. It depends. So the quantity or the size of that brown arrow depends on where I am along the age axis, right? Because if I were to measure this point right here, the distance between the green line and the brown line is much smaller than it is when age is farther out here. Does that make sense? So that random effect is a function of age. Okay, so I have to take age into account with that particular random effect. Now, the deviation from that point up to the actual observation is the error. That's the residual. This is all the model stuff down below, and then however far off the observation is from the model is the error, the residual. That's all that's left. And so that is how you fit a longitudinal model. That's the idea, the basics, the very, very basics. You may need to incorporate curves. If it's not a straight line increase, you may want to add a age squared term or things like that. And you can do that, but this is sort of the basic, good starting point. Now again, now we have three random terms or random effects in this model. So we have the green term, the brown term, and the red term. Each of these has to have its own distribution, and we have to estimate the variance of each of these. So now we have three things that we're estimating.
Sorry, we'll use it. Just go back 2 slides and just show again on the.
This one here?
Yeah.
We're going to make these slides available, right?
Yeah.
So I noticed some of you are trying to take pictures of the slides. We'll make these available if you like, or my email is at the end if you want not only the slides but the do files and things of how to do this in Stata. Shoot me an email. I'd be happy to send you the slides and the do files on the data set and the whole thing. But we're going to make this available on the website as well. So if you want to just...
And this is being recorded. Hopefully it's being recorded. So if you guys can go in, if there's like 2 or 3 slides that was talking that you wanted to listen to that repeatedly until it sinks in, might help.
Yeah. Okay, so that's longitudinal. Any questions about this? It's strange when you see it this way, isn't it? It's not really as complicated as it seems when you look in books.
So sorry, green is the average patient mean from the population mean.
Correct.
Brown is the individual
slope.
Right, individual slope, and then the red is for that one particular observation from that patient's.
Yes. Yeah, let's wander through this again because this is a really important concept. And once you grasp this, you're really home free. So the green line here is the average slope for everyone. That's this beta 1. Well, it's the slope plus this deviation for everyone, but this slope is common to everyone. Doesn't matter which individual it is, they're all changing at that certain rate. But where is it? Back here. That slope may not be the best fit for everyone's cloud of points. So for instance, if this is a particular person's data, we can look at that and say, well, this cloud of points looked like it would be better described with a steeper line. And so I know it's kind of strange to think, but it's easy to do with software that you can actually fit a little regression model, a little regression line for every person in the data set. And that's what we've done here. For each person, so this brown line is unique to a particular individual. If I were to put another individual's cloud of points up, there would be a different brown line there. The green line and the black line would stay the same. It's common to everyone. But we're going to fit a separate brown line for every single person, so everyone gets their own slope. And that's why it's considered a random effect, because it's unique to each person. Does that make sense? It's really cool that you can do this with software. Yes?
Later, the next hour, are you going to go into the different error structures for longitudinal?
No, you're talking about like AR1s and things like that. No.
And that's okay.
Well, there were other things. In fact, Ariel and I had dinner last night, and he was suggesting I remove some slides because I had a lot more slides. I tend to get carried away with slides. There were about 80 slides in the second half. And so we actually went through and thinned the herd, so to speak. So that would be a very interesting topic, actually. And if we have time at the end, maybe we could freeform that, because I wrote a blog a while back on how to simulate multi-level data. And in that blog, I actually show how to simulate data with those kinds of defined error structures, toplets and these kind of AR1 and those kinds of things, because they do reduce the number of degrees of freedom. You don't need as many parameters for estimating the variance. Sorry, no, I didn't do that.
And that's okay.
Blame it on Ariel. He didn't tell me to put it in there.
Actually, I didn't even occur to me to think about the error structure.
Yeah. I have not seen them used a whole lot with biostat people. Econ people seem enamored with those sorts of structures.
Especially the autoregressive ones.
Right. But if things are measured at fixed intervals, like every year, every 6 months, they actually can be quite useful because they do exhibit these patterns. So sorry, no, I don't have that in there.
That's okay. I got your email.
Absolutely. Email me, and if you like, I can send you some more stuff on it.
I don't have the guts to post on listserv, though. The Stata listserv.
Yeah, I tried.
Kind of strict, so.
No, it's a friendly bunch. Anyway. Okay, so any more questions about the longitudinal stuff? It really is this simple. And once you kind of get this notion down, doing this with the software is even easier. It almost becomes, and I think that's why a lot of data analysts don't think about this, because if you've done it a few times, it becomes just sort of an old habit. Oh, I've got age, so I'm not going to put age in there. I need to put a random effect in for age. And you don't even really stop and think about exactly what you're doing anymore. Because it is so easy to do nowadays with software. Okay? So 3-level models, that's 2-level and longitudinal. How about 3? Can we handle that? Well, let's say that we have, let's make this even more elaborate. Let's do a mixture of both longitudinal data and with a nesting structure. So before we had patients within physicians, what if we had repeated observations among patients who are also themselves nested within physicians? Well, that could happen, right? Because you have people in practices, physician practices, where they make measurements of people's cholesterol or whatever. They see these people repeatedly. So it's not an uncommon thing to have repeated observations on patients that happen to be nested within physicians. So how would we go about modeling this? Well, I bet most of you right now could probably go through and do these same slides now yourself. So I have repeated observations within patient, just like I had with my longitudinal data. And then I have patients who are now nested within physician. So within each individual, I have an individual mean. For each patient, I have a patient mean. And then I have, of those patients within a physician practice, I have a physician mean. And now I have these physician means. Let's say I had 4 physicians. I now have 4 physician means with an overall grand mean of the entire sample. So it's just the same idea extended up one more level. So again, talking about the jargon, we have level 1, 2, and 3 now. And now I'm going to be talking about observations I, J, and K, where K, you could use T, the indexes are arbitrary. But K is going to index the repeated observations within the J patients, within the J patients. So J represents patients, I represents physicians. And that's why I put this down here. Really, when I first started doing this, it was the subscripts that intimidated me. I'm like, what does all this keep track of? But that's really all it is. When you start getting overwhelmed by all the subscripts, just remind yourself, this is all it's doing. It's just a way of keeping track of which observation belongs to which patient and which physician and so forth. So just like we did before, we're going to take this basic idea of a single level model and we're going to elaborate on it. So if this was our original observation, I can skip over these now, I think. I'm going to take that observation and I'm going to partition it. I'm crazy with the clicker. I'm going to now partition the random part up into 3 pieces. So if I take that observation, that particular observation deviates from the patient mean by this red amount. That's the error term. And then the green line here represents the deviation from the patient's mean to the physician's mean. And then the blue line represents the deviation from the physician mean from the overall grand mean. So when I write this equation here at the bottom with all these messy subscripts, all I'm doing is I'm saying that that observation is equal to the mean plus some deviation of the physician mean from the grand mean, plus some deviation of the patient mean from the physician mean, plus some error term that's whatever is left over. So that's all I've done. All I've done is taken that same error. It's the same error term from the single level model. Just like you had a regular old error with regression, it's the same thing. We're just chopping it up into pieces. But again, we have to go through and do this for every single observation in the data set, and that's why we need software. So again, I have 3 error terms. I have the distributions. I have to estimate the variances for each of these, which is what we'll see in the bottom of the output. And because this is longitudinal data, now I need to go through this exercise again of flipping it up on its side. So this is exactly what we had before. All I've done is turn it up sideways. I still have the grand mean and the deviation to the physician mean to patient mean to observation. Same exact thing. Now I have I'm just adding in my regression line. Again, same thing, I just have 3 of these lines. Now I have a physician mean as well as a patient mean. Now I'm going to change this to a beta 0 to make it a regression model in my model up here. Now I've added age. By adding age to the fixed part, it allows for this slope again, but I still have 3 of these because I have more error terms at the end. That's all that's doing is bumping these up. Now I'm going to go through this exercise again where I fit the slope for each person individually. So I have the brown line. You see where this is headed. So now I'm back where I was with the longitudinal data. The only additional complication I have is I have this, the physician means. Other than that, it's exactly the same. Okay, so now I fit a longitudinal model for repeated observations within patient, and the patients themselves are nested within physician. And that model at the top would be a simple way of writing this. This might be a good starting point. So again, I'm assuming a straight line change over time. And at this point with my model, I may need to start thinking more about the fixed part. What if I look at the data and there's sort of a curve to it? Very few things have a perfectly linear change over time. Often they have a curve, so I might want to put in an age squared term. Beta 0 plus beta 1 age plus beta 2 age squared, or something like that. I may want to include terms, but this is sort of the basic starting point model that I can use for modeling longitudinal data. Any questions? Okay, how are we doing on time? Are we doing all right? Ooh, we need to move along. All right, you're right. Too many slides. All right, so we still have to estimate all of these variances. Fixed versus random. This is a really confusing thing for a lot of people who've been doing this for a long time. So we've been treating physicians. Let's say that I have 3 physicians, and I do in my data set that we're going to use in the second hour. Let's say that I only have 3 physicians at the top level, at level 3. Well, there are a couple ways I could think of this. One is I could treat it as a random effect where I measure the 3 deviations. The UIJ, I'm only going to have 3 UIs. I'm going to have a deviation from this physician to the grand mean, this physician to the grand mean, and this physician to the grand mean. So I have those 3 deviations, but remember, I'm going to have to estimate a variance for that. Now, if you were going to estimate the variance for something, would you go out and draw a sample of size 3 to estimate a variance? That doesn't really make much sense, does it, when you stop and think about it? I just did it, and you probably didn't notice as it blew by, and I didn't emphasize the fact that I only had 3 observations at the top level. But if you wanted to know the variance of height in this room, you would sample more than 3 people, wouldn't you? That just seems strange. Why would you do that? Well, in fact, that's generally considered bad practice. If you only have 3 observations at the top level or 3 groups, you probably don't want to fit this kind of model at the top level. You probably want to do something like this, where at the top level, you actually estimate a fixed effect for the physicians. And by fixed effect, what I mean is I'm going to move it out of the error terms, and I'm going to move it into the fixed part of the model. I'm going to actually estimate what is that deviation for each physician. I'm not going to estimate it and then calculate a variance for it. I'm just going to estimate what is that deviation. So here, I've written the model out as Yij equals beta 1 x1. X1, the x's here are just indicator variables, so am I physician 1 or not? And so at the bottom, I've written it out as beta 1, 0. This particular observation is a deviation from physician number 2. So this model would be beta 1 times 0, because it's not physician 1, plus beta 2 times 1, because it is physician 2, plus beta 3 times 0, because it's not physician 3, plus these 2 error terms. So the error terms are going to be calculated from each of these fixed points. Does that make sense? So I'm going to actually estimate, rather than estimating their deviation from the grand mean, I'm just going to estimate what each of these things is as the fixed part of the model. Remember I mentioned earlier that this mean, this mu, could represent anything. It could represent a slope of the line. It could be something complicated. That fixed part could be something like that. And this one, notice it doesn't have a grand mean. There is no intercept. I fit what's called an intercept, a no intercept model, or a means, some people call it a means model. So I'm just going to estimate each of those separately and then have the complicated error structure after that. Does that make sense? So that's what I mean by a difference between fixed and random. Yes?
I know there's different rules of thumb, but what do you suggest is sort of like the upper limit or the lower limit for the number of clusters?
Yeah, for estimating as a random.
Yeah.
I wish I had a good answer for that was sort of definitive. There was a paper written in the late 1990s that really addressed this topic, and I think they did some simulation studies to try to show how far off these things can get. By the way, these models are essentially equivalent. If you run them, you get the same log likelihood and things like that. They are just 2 different ways of fitting it. Certainly on the order of 3, 4, 5, you probably want to pick them as fixed effects. I guess the question I would ask myself is, if I have 8, do I really want 8 separate beta parameters in the model? Yeah. And then I have to balance that with, am I willing to take a variance estimate based on 8 subjects?
Yeah.
So where do you draw that line? And I think it also depends on how much variability do you have at that level. Years ago, one of the last projects I worked on as an academic was small town walkability study. And it was a joint project with, I was at Texas A&M University, so we collected data in the South Texas, Central Texas area, Dartmouth University, and University of Washington at Seattle. So we had individuals nested within cities. There were 3 cities in Texas, 3 cities in and around, what's that university that we were in? Anyway, it doesn't matter. It was near Connecticut. And then 3 other cities near Seattle. So we had people nested within cities, nested within regions. Thinking that that region level, because of the weather, that there would be different walking patterns, because when it's really cold up here, you guys probably don't walk a lot. When in Texas, when it's hot, we don't go out much. So we thought there would be variability at the region level, and there just wasn't. So we did estimate it, and it turned out there wasn't much variability at that top level. So we ignored it altogether. If there was a little bit of variability and you had a relatively few number, 3 or 4, in this case, we had 3 groups at the top level. But if you had 5 cities or 5 regions or 6, it might be reasonable to do fixed, because you could get 6 fixed effects in your model, 6 means, and it wouldn't look strange. If you had 15, now you've got 15 indicator variables, and that might be kind of feel so. I'm not sure there is a good one.
And I've heard different rules of thumb, and
yeah,
it's all over the board, right? And obviously, it all depends on the data, and that's the fallback is, well, it depends on the data.
I think that's where the judgment of the analyst comes into play, where what makes the most sense in with that particular data set.
Yeah, it's like a conceptual thing. It's like you extrapolate.
Yeah, right.
So it's like, I don't want to limit it to these 3 institutions or positions. That's not my question.
Right. Exactly.
And vice versa. Sometimes you are listening.
Yeah. Absolutely. Yeah. So that's where I think the judgment of the analyst comes in. You really have to think through what is it exactly, what's the question that you want to answer. So. Which is
kind of what I like about statistics. There really are no set, absolute rules that you can arrested for violate. I mean, assumptions you can't violate. But
Sure. That is one of the frustrating things of having taught statistics for years, is people tend to want hard and fast rules. They want to, like, you'd probably like for me to say 5. Because then it's done. Chuck said 5. I'm going to do 5. 6. It's random, but 5 or less. And that would be neat if there was a rule that I could look up in a book and use it all the time, because it absolves me of having to make judgment calls. But at the end of the day, I think that's our job as data analysts, is to take these tools and then use them in an interesting way to answer questions. Owning a hammer is not enough. Knowing how to use the hammer to build things is what it's really useful for. So.
Can I ask real quick along those lines?
Sure, absolutely.
I've heard that the bare minimum for a nested, a higher level is 2. So like if you have dyads, you can have dyads nested with a family. And I've done that, but it just intuitively, it makes me feel uncomfortable, but is it okay? What's the rule?
We want another rule because Chuck said so.
Dyads make sense. I mean, we definitely want to take into account the nesting of this,
Sure. How much time do we have?
Don't worry, we can.
No, because I have a very interesting story about that, and I'm going to try and make it as short as I can. So when I was a graduate student, I was at University of Texas Health Science Center. I worked for a guy who was actually from here. He was a very famous human genetics professor, and he traveled all over the world a lot doing talks. And so I was left back at the office doing a lot of data analyses and things, and we would communicate by reports via email. Strange to communicate with your boss by email while he's in Russia and South America and China. But that's how we communicated a lot. Anyway, I had this data set. It was genetics, and so we had a lot of correlation. We had a lot of sibling data. This is back in the 1990s. And so I had this data set that it was something like cholesterol. Let's say the outcome was cholesterol, but the data were on siblings. We had sibling data. So I had two. I think there were a couple of triplets in there, but it was mostly dyads of people in this genetic data set. So I had these dyads, and I also, the outcome variable, I think it was cholesterol, whatever, was very skewed. It had a long tail to this thing. And so being a good student, I had paid attention in class, so I knew I had two problems with my data. One was the sort of non-normality, long skewness of the outcome variable, which is going to result in sort of non-normal errors, which back then was a big deal to me. And the other thing is I had these dyads. They were correlated in some fashion, so I needed to account for this in my model. And back then in the 90s, GEE was all the rage, generalized estimating equations. And so I fit this model using, first I used a Box-Cox transformation to sort of smooth out or normalize the outcome so it wasn't so skewed. And then I used generalized estimating equations to fit the model. And I emailed the report to my boss, and he comes back, and we sit down to look over this thing. He literally throws it on his desk. He says, "What is this? What did you do to my data?" And I said, "Well, I ran the model like you asked." And he says, "What did you do to my data? I can't interpret this. What do I do with it?" And I said, "Well," and I rattled off the same thing. I said, "Well, there's a lot of skewness, so I need to make it more normal. And I had siblings, so I got to take into account the fact that it's correlated." He says, "Just go run me a regression model." And I said, "No." I'm a smart student. I know what I'm doing here. "No, I've got skewed data. I've got correlated outcomes, blah, blah." He says, just go fit me a simple regression model. That's all I want." And I protested. "No, you can't do this. You've got the skewness and you've got these correlated outcomes and blah, blah." He says, "Look, you go fit the model and we'll come back and we'll compare the results when you're done, but just do it. Just go to your office and do it." He was my boss. He was also my chair of my dissertation committee. So after I finished washing his car, I went back and I ran this model, and I was going to show him because, boy, I knew what I was doing. I know how this stuff works. So I go back and I fit the model, and I was absolutely mortified that the results, the substantive results, the p-values there was almost no difference in the results. Running just a basic simple linear regression model versus doing this GEE with transformed outcomes and all. That was one of the most important lessons of my life as a statistician, is the fact that you can overlearn some of these things and you can make way too big a deal out of things that are just not. When you're young and you've just learned all these things in classes and you want to follow the rules because we have all these rules and we don't want to appear to be stupid, you take all those things into account. And sometimes people who are more experienced, which he was a genetics professor, but he has a master's degree in statistics from here at UM. Very smart man. He knew this. He had been around the block enough times to know that if you do the fancy stuff and you do the simple stuff, a lot of times they turn out to be pretty much the same. Now, I will say this. They weren't super highly correlated, the outcomes. So if you look at siblings, in this particular case, cholesterol or whatever it was we were measuring, if you looked at the sort of interclass correlation, there wasn't a high degree of correlation between the siblings for this outcome, which is why it wasn't that big a deal in this particular case. Linear regression is highly robust to skewness, which they sort of mention in class, but you don't want to look dumb to your boss. And so there are a lot of these rules that you can sort of break. And at the end of the day, this was a case where, yeah, we had dyads, but they weren't really highly correlated, and we didn't need to do anything this elaborate. I said I was going to make it a short story. I'm not sure that was short, but so yeah, don't overlearn this stuff. Again, there's an element of judgment to all of these. You may not even need to take that third level, the physician level, into account. If you fit a random effects model and you look at the variability and there's almost none, or if you look at this model, if you fit the fixed effects model and beta 1, 2, and 3 look like they're almost the same, you could probably just ignore that level. You have 3-level data, yeah, it's nested within position, but you may not even need to take that into account because there just aren't differences by position. So that was a really long-winded answer to your question. What was the question again? Don't even remember. No. Okay, any other questions about fixed versus random? I wish I had some good hard and fast rules, but I just don't. So this slide kind of points it out in terms of the equations. Basically what we've done is moved this out into here. These things are still estimated either way, right? Because we're going to have each of these. There's going to be a UI for this one, this one, and this one. But in this case, we're going to do it, and we're going to estimate the variability of them. In this case, we're going to move it into the fixed part and just look at them, which is why these models are essentially equivalent. Whether you put it as fixed or random, the log likelihoods of these things, when you look at them, turn out to be the same because they are essentially the same. It's more like, what is the question? Do I want to estimate the variability of it or the actual effect? Okay, I've rambled about that long enough. Models for binary count data, multinomial ordinal data. You can do this. And I actually was not aware of this until Ariel pointed it out. I think at some point I knew it, but I don't really use this very often. Let me start again. You can fit multi-level models for all kinds of outcomes, binary outcomes, if you have count outcomes, if you have ordinal or whatever kinds of outcomes. There are a whole collection of distributions that you can use to model these. So Gaussian is the continuous, the normal kind, continuous data. But you could have Bernoulli data or binomial gamma. Gamma is very flexible for modeling all kinds of things, negative binomial and so forth. And then you can choose different link functions. If you're familiar with the ideas of generalized linear models, that's exactly what this is getting at. So you have different distribution families that you can use to describe your data and different link functions that you can use to model your outcomes. So for instance, if you had binary data, the logit link is very common for modeling binary outcomes. The logit link or logistic regression is typically used. And we're going to see how to do that in the second hour. But there are a whole bunch of these. In Stata, we have this general command called MEGLM where you can fit all kinds of different outcomes like this, different models for different kinds of outcomes. I have a tendency to use the specialty commands in Stata. For instance, there's an MELogit command. I tend to use those because there's some other options that are specific just to MELogit. MEGLM is generic across all of these, and it's very flexible. But there's some cool things. There is an MELogit. There's an MEPoisson. There's an ME other things. So I tend to use those. But you can absolutely do this for non-continuous outcomes in Stata. Survival data. How many of you work with survival data? Anyone? Yeah, so often you end up with nested survival outcomes. So for instance, same thing with physicians. You may have a bunch of patients nested within physicians. And again, these outcomes could be influenced by the physician. You go to a top-notch cancer oncologist, and you may live longer than if you go to some guy in your small town doctor. So there may be an effect of the physician on the survival outcomes, and you may want to take that nesting structure into account. You can do this in Stata. By the way, the graphs here are just each individual. So this is patient one. Patient one goes out for about 40, 45 days and dies. The X's mean they're dead, and the circles mean they're censored to survival. That probably looks familiar to you. Anyway, so we may want to take the nesting into account with survival data as well, and you can do that with the MEST reg. Yeah, MEST reg? I think it's MEST reg. Anyway, we'll see it in the second hour. It's on the slides. Structural equation modeling. This has become increasingly popular in the behavioral sciences, SEM for short. And in Stata, we not only fit regular continuous outcome structural equation models, but also what we call GSIM, generalized structural equation models, which allows you to fit multi-level latent variables with non-continuous outcomes. So for instance, now why would we want to do something like this? For starters, people who work in structural equation modeling like to draw these path diagrams. They're called path diagrams. So each of these blocks represents an observed variable. So we observe cholesterol, we observe a patient's systolic blood pressure, we observe their centered age, CAGE is centered age, or their sex. These latent variables with the double oval mean that they are multi-level latent variables in Stata. That's the sort of the symbol that we use for them. So we can use these as random effects terms in our structural equation model and build longitudinal or multi-level models this way in a structural equation modeling format. What's cool about switching into GSIM is now I can fit systems of equations. So in this case, I have an outcome here, which is cholesterol, and I have an outcome, which is systolic blood pressure. I can model both of those simultaneously. Econ people, this is more natural to econ people, fitting systems of equations. So rather than having one, y equals whatever, there may be y1 equals some equation, y2 equals some other equation, and y2 could be in y1's equation. It's a very natural thing to economists, the notion of systems of equations. So you can do this in Stata with SIM. With GSIM, you can even have systems of equations where the outcomes are not the same kind of data. So here I have a structural equation model where I'm assuming that age is influencing survival time, and age is influencing high blood pressure, and high blood pressure being a binary outcome now. And age can influence high blood pressure, but high blood pressure may influence your survival time, right? So that's another equation in my model. I also might have age influencing your cholesterol, because that goes up over time, and cholesterol may influence your survival time. So I can have these systems of equations, and because of the multi-level latent variables, I can fit multi-level repeated measures kinds of systems of equations. So if you find yourself doing this sort of thing, check out structural equation modeling, some package, but in Stata in particular. Bayesian, if you have a Bayesian bent, Stata now as a 14 does Bayesian models, and you can fit the syntax looks messy, but it's not our fault. It's just inherent to Bayesian statistics, because you have to have priors for all of the parameters in your model. So it can be done. If you want more information on this, some of this is in video format on our YouTube channel. Stata has a YouTube channel that has tutorials for how to do these things. And I've written several blogs on like how to simulate multi-level data and how to fit these kinds of models using these slides. So it sounds like we better wrap it up. But is this, you guys are pretty much staying into the second hour. Can we